Hello. So this is a class on the quantum information and quantum computation theory. And my name is Jung Hoon Han. So I will be teaching this course for the first time and probably for the first time at this university. And the reason why I want to introduce this class is because of the following historical motivation. So the motivation is that that perhaps the 20th century. All right, this is too thick. Is about the century of technology, of course. And if you think about it, quite a lot of this technology is based on quantum mechanics. Okay. So some of the most outstanding examples of the quantum-based technology is, of course, the computer. Right? Computers are based of chips or processors. And these processors are basically semiconductors. And these semiconductors are working the way they do because of the principles of quantum mechanics. So until we have figured out how the electrons propagate through a certain kind of material, we weren't really having any handle on on the the physics and the working principles of these semiconducting materials. And without those understanding and the ability to control the electron flow through these semiconducting materials, of course, there would have been no processors, and therefore there would have been no computers. Now, there are lots of other examples of quantum-based technologies that we use on a daily basis, like laser, and so on. But I'm not going to spend too much time listing these examples and the physics principles that lie behind these, because this course is really much more about the quantum information and quantum computer, which is one particular and probably the most exciting realization of the quantum information sciences that's forthcoming in the 21st century. So we are very much into the 21st century, and we're about roughly 100 years from the invention of quantum mechanics. Right, the so-called Schrödinger's equation was invented about 1927, and there were also important discoveries by Heisenberg around 1925, something called the matrix mechanics. And so on. So around the mid 1920s is where all of the important principles of quantum mechanics was born, and we are now in 2021. So that's a good 100 years of separation from these early days of quantum mechanics. And so we have been making very good use of the principles of quantum mechanics, which were invented around the mid 1920s throughout the rest of the 20th century. But as we move deeper into the 21st century, what I believe is happening is that we're going to be using or relying more and more on the slightly different aspects of quantum mechanics. And these slightly different aspects may be called the entanglement, or maybe quantum coherence, and so on. And I will try to elaborate on these concepts as the class evolves. But for now, it's probably sufficient for you to just remember that these concepts and words will play a pretty important role in the course of this lecture. All right. And on top of these so-called entanglement and coherence aspects of quantum mechanics, we throw in a vital new ingredient called the information. Okay. We are more or less familiar with the idea of information, especially information that is stored in the digital form, right? So strings of ones and zeros like this represent, let's say, alphabet A, and then maybe this will represent another alphabet B, and so on. So there's a kind of one-to-one mapping between a certain string of binary numbers and the more familiar way of storing information in terms of alphabets like ABCs or maybe 기억, 니은, 디귿, or things like that. Okay, and then there is the physical implementation of these zeros and ones. Okay, so when a piece of when a part of the circuit is, for example, is in the on state, we make a convention to associate this on state with this binary information 1. And then if this piece of circuitry is in some sort of off state, we agree to refer to this off state as a binary information corresponding to 0. Okay, so on the left-hand side is some sort of mathematical theory of information. And then on the right-hand side is the physical implementation of the theory of information. Okay, so of course we need both of these, both the physical implementation and the mathematical theory behind such information sciences in order to come up with something that we call the computers, or in general digital information and the entire civilization built on such digital information technology. So when we normally talk about computer industry or semiconductor industry, we're focusing on this aspect. But before the computers were first made, there had to be a formulation of this kind where smart people try to come up with some mathematical foundation of representing information in terms of some mathematical objects. The mathematical objects being these zeros and ones or binary numbers or simply called bits. Okay, so now what we try to do, um, okay, sorry. Yes, let's add one more page. Good, yeah. So now what we try to do is to try to store information in not bits but quantum bits. So first of all, you have to be wondering what is quantum bits or qubits. And as we go along, of course, I will be trying to make this notion more precise, just exactly what I mean by qubits. But let's for the moment suppose that there is such a thing as a qubit, and there are huge efforts worldwide to efforts to make a physical implementation or just physical qubits. So what that means is that people are trying to make a machine that actually make qubits and then use these qubits to store information in a quantum mechanical manner, and also to control this information in a quantum mechanical manner. And the consequence of all that is a way to process information, which was not possible with the classical computer. Remember that the classical computers are machines that do certain operations using these bits, zeros and ones. And there are certain kinds of mathematical manipulations that are much more easily done using the qubits rather than bits. And therefore, for these sort of mathematical calculations, it is far more advantageous to use a quantum computer to do that calculation than trying to put that same calculation on a classical computer. So that's pretty much the reason why a lot of people are working very hard these days to come up with a nice working quantum computer. Okay, so much like the, I'm trying to find the, sorry, where is that slide? Okay, I lost that slide. Okay, here it is. So much like these two different aspects of a classical information sciences, namely the mathematical theory of the information sciences And then there is the physical implementation of that mathematical theory into some specific hardware, which we nowadays call the computer. So in order to realize a sort of a quantum computer civilization or a new sort of technology that's based on quantum computer sciences, we will have to repeat or mimic these two progresses that have been made in the previous century. So that means what we have to do now. Sorry, I keep switching back and forth. So what we have to do. So what we have to do is to develop some theory, of quantum information. Okay, that will be the first phase of the work that we have to do, and then the second phase is to do some physical implementation. And that's essentially equivalent to building a quantum computer. Okay. So we're not going to be doing too much of these practical side of the quantum information aspect. For this, there is another lecture being offered in the second semester from Saint. I think the title is something called Quantum Computer something. And this is offered during the second semester. And in this course, you will hear from also from experimental people who are trying to actually build some sort of quantum computer. Okay, so I'm just telling you that there's this course that's available for you to look into in case you really want to go deeper into this new and exciting discipline. But what I'm going to do in this class is mainly to focus on this first aspect, the theory of how we can store information using the quantum mechanics in a rather explicit manner. Okay. So where's that textbook? Okay. So I will be writing up this note as we progress. So there will be no specific textbooks for this class because I'm trying to put everything I know and everything I want to share with you into my personalized note. And this course lecture note will be updated from time to time, maybe once every week, and uploaded onto iCampus. So lecture will be updated and uploaded maybe once a week. So there's no need for you to print this out every week, every time the note gets an update. I know that many of you guys just want to read these documents online rather than in some print form. And that's probably what I would expect you and encourage you to do in the course of this lecture. But just in case you want to have some textbook by your side, what I would have in mind for the most part of my lecture as a reference will be these two books called the Quantum Computing from Linear Algebra, etc., etc. And I think you can even download this PDF from some source. This is not even illegal. You just have to type the name of this textbook into Google, and it will direct you to some website that has this PDF file available for download. And I don't know about this book, whether there's a free PDF for this. This is some sort of a classic in this field. Remember, note this date that it was published. It was the year 2000. And this is the kind of year when very few people were paying attention to this quantum computation stuff. Rather, I should say the year 2000 is about the time when some people here and there began to realize that perhaps quantum information could be the next big thing in physics and in science in general. And they began to pursue this subject seriously. But the number of such people were very small compared to people doing a lot of other things. But clearly, the importance of quantum computation and quantum information has grown dramatically since then. And I personally believe that this quantum computation should really be a part of the physics curriculum forever. I mean, at least in the next few decades. And so there's this book. This book is well over 500 pages long. So this is an enormous book. This book is a little bit shorter, but it's quite dense. So dense means that if you just try to read this book from cover to cover, it's not going to come across as an easy read. So what I'm hoping to do is to provide my own version of the story, which is somewhat simpler than both of these textbooks. Okay, so maybe the hope is that if you finish listening to my course, then you still want to learn more about quantum information and quantum computers, then maybe you can move on to one of these books for further study. Okay, so the plan of this lecture is the plan of this course is to basically give lectures. That's what I do. And then plus some homework from time to time. And then perhaps 2 exams. And because I've never taught this class before, and no one at this university has ever taught this class before, so when you try something out for the first time, I think it's a good idea to be slow, cautious, and slow. So I will be teaching slowly. But still, if you find my lecture to be too fast or incomprehensible, just post your questions on iCampus. I will be logging into iCampus once or twice a week just to make sure, first of all, to upload my lectures, and also to make sure that that if there's any questions that you have and post it on the iCampus, I take notice and try to answer them as fast as I can. So my response to the questions that you raise on the iCampus will be to try to post my answer videos as soon as possible. Okay, so that although it may not be so easy for us to interact face to face, still we can interact through this virtual space without too much time delay. Okay, I guess that's it.